All right, everybody. Thank you so much for enjoying your break and being back. We have Daniel Gruss and Jonas Juffinger here, all the way from Austria at TU Graz. They're presenting SUIT. Recently, also, I want to point out, they just presented Snail Load at Usenix, and Jonas here is wrapping up his graduate degree, and he's moving on soon. So congratulations, Jonas, and welcome. Thank you so much for being here.
So welcome to our talk about SUIT, secure undervolting with instruction traps. We will also talk about another work that we have done in the most recent years. We are from Graz University of Technology, and I'm a professor there, so I have worked on security for quite some time.
And I think today you will hear about two visions for computer security. And one is about the future, and one is only about the past. And the vision for the future includes having a plan.
Yeah, and you think you have a plan, right? Okay, so let's take a look at the plan. A plan for security, a plan to destroy performance, a plan to waste endless amounts of energy. We're a failing community, the security community, right? What we see if we look at the energy forecast of our modern ICT is that we are reaching 25% probably just a bit after 2030. This estimate was from 2016. This was before Meltdown and Spectre. This was also before the big Bitcoin bubble. It was before the AI hype. Probably it's looking way worse by now. Let's take a look at where security is. A single security patch from 2018 against Meltdown. We estimated that the performance overhead for that one is 5%, and there were also some measurements on the energy costs. So if we just take 5% ballpark estimate, and it affects basically all the machines out there. If you run the numbers, you get to a worst case estimate of something like 0.09% of global electricity consumption. Single patch. That's a bit much, right? But what about 2030? If we have a single patch that has this much impact in 2030, same calculation, we're at 0.4%. A single patch. That's not sustainable, right? Now, some of you might say, yeah, but we always figured out how to do it. We have Moore's law, right? And it's going to fix everything. But the problem is Moore's law is dying, right? It's going to end. Yeah, people don't want security, that's clear. They want performance. OpenSSL just opened their implementation again, and they now let millions of side channels back in. Not millions, actually. Yeah. So one question that comes up here is, for instance, Rowhammer. Why is Rowhammer still not solved? That's from 2014. Jonas started talking about security. He's going to do all these wonderful things. Why hasn't he done it? He's been there for 3 years, right?
Yeah, it's pretty difficult. Let's talk about some background stuff here and Rowhammer for a second. So, who have you heard of Rowhammer already? It's probably pretty well known at this point because, as we already said, it exists for 10 years. So what you see here is the DRAM on the left, and that's a single bank of the DRAM, and it stores all your data in a computer you're working on. And it's built like this. It has different rows, a row buffer at the bottom. And what Rowhammer does, if you access two of these rows, or some of these rows, it copies data into the row buffer to go to the CPU. If you do this with a very high frequency, you increase the speeds these cells discharge in the middle. And what happens is that bits can flip. Without actually accessing this data in the middle, we now had bit flips. And this is bad, because you can attack computers with that. You can do a lot of bad things.
Yeah, but this is old stuff, right? We've known this, and yeah, you can do this in different ways. There's single-sided hammering, which you can use, where you basically just hammer random addresses, and then you see bit flips next to one of those rows, right? Yeah.
Yeah, this is what they initially found, and it's not very effective. So a year later, some researchers from Google actually found a different hammering method, the one we also saw at the beginning, where we actually sandwich one row in the middle with two aggressor rows, we call the yellow ones. And here we get a lot more bit flips in the middle row. So this is, the problem is getting worse, right?
So, but we didn't get to know each other today, right here on stage, right? But we already know each other before. And the first time that we worked together was also on rowhammer.
Because all the literature back until then, I think it was 2017, they were hammering 2 rows in the DRAM. And this is actually what made sense on how DRAM is built, why you have to hammer 2 rows. But this, we figured out in 2017 that this is actually not true, that you can just hammer a single row and still create bit flips. So we are just activating the single row and we saw bit flips. And there's a problem with that because we didn't hammer 2 rows, we were able to break all mitigations that were published until then because they assumed 2 rows had to be hammered to actually cause bit flips.
All right, so maybe the problem is that we have a lot of misunderstandings here. If we think about performance and security, we often want to optimize the system for performance, not necessarily for security. We could add things into our systems like ECC or other mechanisms against row hammer or against memory corruption, just add a bit more reliability, right? And that solves the problem then, right? Why not ECC everywhere? We could do that. What does ECC give us? Yeah.
I mean, it gives us some security, but what incentives does it actually create? Okay, so we have ECC actually for quite some time in mobile devices, low power DDR4, and these standards have ECC on chip, which is pretty nice. And so ROHAM mobile vendors had a great idea. So with all this additional security, why just not optimize performance a little bit more?
Oh no, a new rowhammer attack. So what is this one about?
This is half double. So they added mitigations for rowhammer, they have ECC everything, and they felt pretty secure. And then researchers from Google, and we also published this with them, found the half double attack. And this one is quite funny because it actually uses the mitigation for rowhammer to hammer. So the mitigation helps us in this case. And what we do is we activate these rows that are 1/3 out, so the victim row is still the one in the middle. And now with this mitigation, it's called TRR, target row refresh, it prevents rowhammer by refreshing the neighboring rows and keeping the values correct. But what this actually does is, or additionally, these refreshes here from TRR, from the mitigation, help to increase the blast radius of rowhammer and still flip bits here in the middle. So because of the mitigation for rowhammer, we were now able to hammer from a distance too, quite reliable. And
yeah.
This is bad.
And that's also the core of the problem here. We're trying to optimize systems for normal usage, no adversary. We've just seen in talk before, oh, we don't need encryption, we don't need authentication because there is no adversary in the system, right? And this is also a problem in our everyday computers and servers where we just say, oh, it's normal usage. So we assume what is still reliable, but we don't really change the game. If we add ECC for an attacker, it doesn't matter whether there is ECC or not. It doesn't matter because you're not changing the game at all. You're still 1 bit flip away from a full system compromise. If you have that 1 bit flip, you compromise the system. Oh, that was one too much. So the attacker does not really care whether this is with or without ECC. And this is interesting because this curve is something that we don't see in a lot of other areas. So I will just take one example here. I could go for the DRAM refreshes, but to illustrate this nicely, I went here for the clock frequency and the operations per second. And I could optimize the system. Well, I can run it in anywhere on this frame. I can run my computer slower than what it is sold. It's sold at 100%. That's the speed that the vendor set up. I can also overclock it. then it gets unreliable. And I can do the same thing with DRAM. I can reduce the number of refreshes. It gets faster, but it gets unreliable. So I have this pretty linear curve there. At some point it becomes unusable, at some point it's dead. That's how it works, right?
But we could do a lot better than that. And this is what I imagined when I said we have a new future for computer security and efficiency. So what if the curve would look something like this, where you have the same thing, it's still reliable, you run with 100% of the raw performance, but then if you increase the performance further, there's some mechanism that actually decreases the effective performance, but keeps the system reliable. So you add some security there that doesn't cause the system, or that prevents the system to become unreliable or unusable. But of course, the system has an overhead, and there's some sweet spot here where the system is pretty performant and never becomes unreliable. So by adding this security, the overhead, we can still gain some performance and always stay secure.
Okay, so this is interesting. So you're saying you can run a system faster and more efficient at the same time?
Yes, and secure.
So security for efficiency, basically. Well, if that works, I'll be eating a dog.
Okay, let's see how this works. Imagine that. So what we have right now is if we increase DRAM energy efficiency, for example, by decreasing the refresh rate or lowering the voltage, performance can increase, but we also increase the bit flips. And we don't want bit flips, of course, because the version system security, rowhammer attacks are out there. What if bit flips degrade performance without degrading security? No security impact.
Yeah, but that's hypothetical. You can't do that, right?
And I will show you now how we did that. So we go to the sweet spot then, and then we have the best energy efficiency for the best performance.
So you already saw a nice summary of what CSI rowhammer does. The idea is that we introduce a cryptographic MAC instead of the ECC code. Also, that's kind of my goal. On the long run, I want to make sure that we stop using those old codes and use cryptography instead for error detection, because it's much more powerful and much more efficient. We can detect any number of bit flips. If you think about it, any cryptographic protocol will be able to detect any number of bit flips. If you have a cryptographic MAC, a hash, any number of bit flips, unless you break the cryptography behind it. And then the question is, of course, how do we correct this? And for that, we use a brute force search. That sounds very inefficient.
Sounds pretty bad, right? But the problem is cryptographic MACs cannot correct bit flips. That's kind of their goal and their design. So we don't know where bit flips are if we find bit flips. We saw this diagram already. It was extracted from the die shot, as you remember. So what we do is we compute this MAC, we put it on the DRAM, so we just use the ECC DRAM with this additional memory for where current computers use ECC codes. We just put our MAC there. And on every read, we compare the MAC with the computed one from the data, and we know if any bit flips happened. And to correct bit flips, we now use the brute force search. Oh, sorry. We can correct a single bit flip in hardware, and what we do is we just try, we flip a bit, we compute the MAC, we flip the next bit, we compute the MAC until the MACs match, which is, for a single bit flip, quite efficient. We can also do 2 or 3 bit flips, which is quite efficient. And we can go to the operating system, so we see the numbers here. So we can do 5 bit flips in 260 milliseconds. So
and this is pretty impressive, because ECC can only do the first row. It halts the system on the second one. You will never get back from that.
Even if we cannot correct the bit flips, they never go further. So if the computer, for example, can correct a bit flip, the operating system can just shut down. So the worst you can do with this is denial of service if you manage to get as many bit flips as an attacker, but you can never compromise security. So denial of service is the worst you can do, which is quite okay in many use cases.
All right, but what about the security of this?
Yeah, it's pretty secure, so we use this cryptographic MAC. So there is, of course, a chance of silent data corruption everywhere. We always see bit flips, and we did the math on like how often does silent data corruption actually happen, like your cosmic ray coming in or something like that. And then the silent data corruption actually producing a second pre-image, which means different data that creates the same cryptographic MAC. And this doesn't happen very often. So with like normal silent data corruption rates on a single machine, this happens like once per 10 to the power of 9 billion years. So that's quite good. If we have a super gifted attacker that is able to row hammer extremely efficiently and create bit flips all the time in the DRAM, and the attacker wants to create a second pre-image through these, so the attacker is able to do, I think the math was a few like bit flips per second, and every time there's a chance of getting a second pre-image. Even if this happening, if it does it for a full year, is like tiny with 10 to the power of minus 4%. So it's pretty secure. The guarantees are there.
If you have a lot of bit flips, then there is a small chance that you have a wrong correction. But in that case, of course, 8-bit errors, this is something that modern systems can't handle currently. They can handle a single bit flip if they have ECC RAM. 8-bit errors is way beyond that. We also looked at the performance of that. It looks pretty okay.
So now, of course, we have to compute the MAC on every memory access. It takes some time to do this cryptographic computation. But we have a performance overhead of less than 1%. So that's
So anyway, my vice presenter now had so much talking time, I will switch back to a different topic, and I want to talk now about overclocking. Who overclocked their computer at some point in the past? Yes, some gamers here, right? Yes. Overclocking is great. It's great, especially if you left the voltage at the standard level and just overclocked the CPU, because then you did something good for the environment. Because you got more performance out of your computer for the same voltage that you let into the circuit. There's another mechanism that is the counterpart to overclocking, and that is called undervolting. Who undervolted a system? Okay, undervolting, interesting technique. So I had to undervolt my laptops in the past, and one question that I have for you is, what happens if you undervolt the system? Who thinks it will become slower if you reduce the voltage? Who thinks it will go faster? Who thinks the speed will stay the same? Okay. What happens? Actually, it gets a lot faster. So you're saving energy. In my case, my laptop, when I got this fresh 13 hours battery runtime on Linux, that was pretty good. Undervolted it, 23 hours. That's significant. So I get a lot of extra battery runtime. You get higher performance as well. So why do we get higher performance? Because actually modern processors just use the TDP to determine how fast they can run. The TDP is basically measuring how much energy is the computer using right now. And if you're using less energy because you reduced the voltage, it can clock higher for longer times. So you actually increase the performance of the CPU a lot. Yeah, and I did this for more than 10 years by now. I started this in 2009, and I've undervolted all my systems since. Yeah.
But what about security, Daniel?
Yeah, of course, he only cares about
right?
security, right?
There's some problems with that if you undervolt.
Yes.
And Daniel also actually showed that with the plundervolt attack.
Yeah, right. Damn it. There was something.
I'll show you some code here. This for loop. It's pretty boring, so what it does is it computes a multiplication of these numbers, and then it runs this while loop as long as the computation causes the same result, which means that it should run forever, right? Let's see what happens if we do this with a CPU while we undervolt the CPU.
All right, we're undervolting minus 250 millivolts. The base voltage here is 750, so we're undervolting quite a lot already. And we have an error in the calculation. That's unfortunate.
That's not only unfortunate, that's pretty bad.
So
there are many cases where you don't want to have just different results.
But in terms of performance, this is amazing, because look at this. I'm saving 50% on the voltage. That's insane. Look at this plot here, how much voltage I can save. So much energy. Who thinks of the environment? The ice bears, polar bears, the penguins, right? Yes.
So why don't we just do this on all computers? There are, of course, many reasons, right? You have like process variation. You cannot do this on every CPU the same way. The manufacturer's opinion is...
So you care about security. Then
Yes.
how do you make this secure?
So we want to do this, right? We also did some measurements on this, a bit more scientific than some Intel benchmark thingy. So we run SPEC CPU and undervolted the CPU, and here you can see mean power goes down. That's the red dotted line from 90 watts to 77 watts. So that's a desktop CPU. And actually, frequency increases because of like the TDP and thermal limits. And you can also see SPEC benchmark, so SPEC CPU2017 benchmarks actually increasing by, on average, 3%. So we want this.
So this is interesting.
You can also see it here, where we have like, 3% frequency increase, 16% power decrease.
Which is interesting because we expected, especially for the first two rows, we expected a significant decrease in power consumption. But what we actually got was an increase in frequency from reducing the voltage.
Yeah. But, as we just said, there are reliability issues. Your computer can just hang if you undervolt it. And even worse, there are security issues.
Right. I think in general, reliability and security, we have to rethink about what these terms mean. So in the past, we separated them and said, we have an architecture, reliability on top of it, and then functionality on top of it, and so on. At some point, security at the very top. That's completely wrong. The assumption of reliability is normal usage, no adversary. We don't have systems today anymore where this is true. Reliability doesn't exist anymore. Reliability has become security. If you don't ensure security, it's not reliable. All right, so how do we ensure reliability and security here while also undervolting?
Why does undervolting even work? That's a good question. So why don't CPU vendors why don't they set the correct voltage? Why is there this huge?
Why do they do it wrong? It's stupid.
Why do they do it wrong? Intel doesn't know anything. I mean, there are good reasons to do it like that. And so what every IC needs is a voltage guard band, they call it, because there are many effects, like process variation, where every CPU is just built slightly different. You have aging. The voltage requirements of chips actually increases when they get older, because the transistors just degrade and become slower. There are, of course, temperature influences. So when your CPU is hotter, it needs more voltage than when it's colder. And there's this one thing that we found, is this variation in instruction voltage. So there are just some instructions that need more voltage than other instructions. And it typically depends on the complexity of the instructions, very simply. So a simple AND or XOR computation is not very complex. You have a few transistors and that's it, so not a high voltage requirement. Integer multiplication, on the other hand, multiplying two 64-bit integers, that's pretty complex.
Yeah.
And
so we looked at
it needs a higher voltage, and this is what we see here. And we, like in the Undervolt paper, they actually measured 150 millivolt variation. So the integer multiplication instruction required 150 millivolts more than.
So we looked at a lot of different instructions, and we don't have the time to go through all of this because I think we are already 30 minutes in the talk. There are a lot of details around this paper. Maybe you can just very briefly go over them.
So we have this hardware software co-design where the operating system takes an important part in the whole thing. the operating system can disable opcodes. So for example, it can disable the multiplication instruction, and then the CPU just checks if this is executed or not, or if it is disabled or not.
So some instructions cannot be executed anymore.
Yes, so in this secure mode, some instructions cannot be executed, but then you can undervolt the CPU. And if one of these instructions is still executed, like integer multiplication, we can do stuff. For example, we can emulate the instructions.
So you want to emulate instructions?
Yes.
Illegal instructions. So now he wants to do transformative operations on illegal instructions who are in some kind of prison or jail mode. Yeah? Very odd.
Yes. But what we can also do, we can just increase the voltage again. So if an integer multiplication is found in the instruction stream, we just put the voltage back up.
Yeah. But this.
So we have these things now. We have these two DVFS curves, so where we have the clock frequency and the voltage, and the conservative one is that you have in every CPU nowadays, and we add this efficient one, and then we just jump between the two curves whenever needed. By changing the voltage or by changing the frequency, we can change between the conservative and the efficient state.
Yeah. Or you stay on the lower curve if you want to emulate it. All right. Yeah, for some instructions this doesn't work, so we would have to also increase the latency for some instructions, but if we do that, we're good. Which gets us back to basically the overall savings that we had with Suit. We have a few more slides that you can look through if we put on the slides afterwards, right? Yeah. That's good. Yeah, the IMUL latency. IMUL is one of the instructions that we had to make slower.
Yes, so we had to make, if you want to emulate IMUL every time IMUL is executed, that doesn't work because there are just way too many integer multiplications everywhere, like array lookups and just calculations out there. So what we actually do for IMUL is we make it one clock cycle slower and decrease its voltage requirement with that. And making IMUL from 3 to 4 clock cycles isn't that bad actually. The average performance overhead is 0.03%, so that's almost nothing. And the worst case was the X264 benchmark video encoding, and it saw a 1.6% performance overhead by making IMUL slower and therefore secure. So with the secure IMUL, no security issues with undervolting.
All right. Yeah, we also looked at the overall savings that we can get there, and you can see how the performance and the efficiency improve with this technique. We have this bigger table here where we overall
see... Many numbers in the paper.
Yeah.
Many numbers in the paper.
Yeah.
And so our best result, I just want to point out this one, is we can get up to over 20% increase in efficiency and 3.8%, that's on the bottom here, increase in performance. So your CPU is just faster and more efficient, basically.
For free.
For free.
And this is counterintuitive because we're adding security. The system now does more than it did before. It has more security guarantees, but at the same time, it's faster.
We are at this sweet spot that we saw before.
All right. And with that, the time has come for closing statements, and Vice Presenter Jonas, we begin with you.
So we have these decade-old problems like Rowhammer. Rowhammer was founded in 2014. It's 10 years, and it's still not solved, sadly. We propose CSR Rowhammer. Let's see if some CPU vendor wants to build something like that. Would be nice. And it works because it uses principal security. We just want to ensure data integrity without looking at Rowhammer in detail. And if we do this, we can actually increase efficiency because now we have guaranteed security, and we can find this sweet spot where the system never becomes unreliable, always stays secure, and we can optimize way better. And there are probably new areas where you can look at that, right, Daniel?
Yeah, definitely. If you take a look at the two proposals that we had, they have lots of opportunities to explore what else you can do. For instance, the correction. We do a stupid brute force correction. Maybe there's more intelligent things that we can do. For the undervolting, this is a very naive approach to just disable some instructions. Maybe there is something more intelligent that we can do. But it's interesting to point out that there is a potential in this direction, and I think this is a big unexplored area that we need to focus on more. Yeah, of course, the papers were funded by several companies and public grants, and with that, we are already at the time for your questions. Thank you for your attention.
What would happen if, I guess, you're switching between your voltage receivers? What if someone specifically made, I guess, a binary that causes you to switch between your two voltage receivers every other instruction? Does this have any issues with the hardware or overheating?
Yeah. So we don't switch for every instruction. We did some measurements on how long it actually takes to switch the voltage, and it's pretty slow. So we are in the range of 300 microseconds to switch the voltage. So what we do is when we switch the voltage to the conservative, voltage, we don't switch it directly back. We stay at this voltage level for quite some time, because usually these instructions come in bursts. So maybe you do some encryption and you run a lot of AES and R instructions. They come in a burst, and then we just stay at the higher voltage. And if we don't encounter any of those instructions for quite some time, we go back to the efficient one. So we don't have these super frequent changes in voltage.
All right. Otherwise, thank you all again, and we are happy to chat with you.
Have a nice break.